Hello and welcome. Welcome to the second day where we continue talking about sound. Yesterday we looked at the examples which are found in your course book and I explained each one of them. And then I gave you some assignments. I gave you some questions to do. And in this particular video, we want to go through these questions. And before we go very far, if this is your first time on this particular channel, just consider subscribing and share this video with your friends. And let's go to the first question. The first question in the course book is actually question number 2. Question number 2. And the first part of it is asking us, how does sound differ from plain water waves? And then the second one is a calculation over there. Is a calculation, and I would like to go straight to the first part. How does sound waves differ from plane waves? First of all, you should realize that sound is a longitudinal wave. There are two types of waves, longitudinal waves and transverse waves. So while sound is longitudinal, water waves are transverse. Okay, then when it comes to sound, we find that it can travel through gases, it can travel through liquids, it can travel through solids, but water waves, even from the name, they can only travel through one medium, which is water as a medium. The speed of this sound in different media depends on the type of media. Okay, and the speed is highest in solids while it is lowest in gases. All right, but when it comes to water waves, the speed will depend on the depth of that particular pond. If, for example, it is on a ripple tank where the water is shallow, then the speed is slow. Where the water is deep, then the speed is fast. Those are some of the differences that we can be able to think about. However, both of them are waves. Let's look at the part B. Part B. In part B, we were given that the range of audible frequencies, that is, audible frequencies are those frequencies which can be detected by the human being, the human ear. If you can be able to hear a certain sound, then the frequency of that sound lies within the audible range. Okay, if it's outside that range, especially if the frequency is higher than 20 kilohertz, then these are frequencies which you cannot be able to hear. They are referred to as ultrasounds. Ultrasounds. They are sounds, all right, but they are beyond this particular range. They are referred to as ultrasounds. If the speed of sound is 340 meters per second, what is the corresponding range of wavelengths? So if the frequency is 20 kilohertz, we are going to use the equation wavelength is equals to speed over frequency, and that gives us 17 meters. When we use the same equation with the 20 kilohertz, we find that we are dividing 340 by 20,000 and we get 0.017 meters. So the range of wavelength is from 17 meters all the way to 0.017 meters. That is the range of the frequencies. I mean the range of wavelengths. Let's look at the next one. So in question number 3, we are given that a man standing in a gorge between two large cliffs claps his hands at a steady rate and hears two echoes. The first comes after 2 seconds and the other comes after 3 seconds. So it's clear that he's not in the middle. So he's near one of the cliffs, and the shorter time will correspond to where he is closer to the nearest cliff. Okay, so, and I've been able to draw some kind of diagram here just to illustrate this. So this is 2 seconds. So the distance between the two cliffs will be D, capital D, so that if he is closer to one of the walls and we call it X, we call that distance X, then the other one will be D minus X. So that one is understandable. If this one is x, then this one is d minus x. Right. So the shorter time, which is t1, 2 seconds, will correspond to the distance x, while the longer time, which is 3 seconds, will correspond to the longer distance, which is d minus x. So by using the equation v is equals to 2d over t, 340 is given as a speed of sound in air, is going to be equal to 2x over 2, in which case we are going to have x being equal to 340 meters. When we use the same equation for the other side, for the second cliff, where we have v is equals to 2d over t, 340 is equals to 2 into d minus x, but we already know that x is 340. So after multiplying both sides by 3, then I'm going to introduce this one over here. When I open the brackets, I get 2d minus 680, and that is what I get. 1020 is going to be equal to 2d minus 680. When I move 680 to the other side, I add onto it, it becomes 1700. However, it is 2d is equal to 1700, therefore d is 1700 divided by 2, which is 850 meters. So you find that it's just understanding the question, and you find that in all problem solving, I try to draw a diagram so that I now reason out from that diagram, and then in my diagram using certain abbreviations, certain symbols to stand for certain physical quantities. You can also do the same because it's not easy to engage in this kind of problem solving without having a mental appreciation of what you are dealing with. What kind of picture are you dealing with? And then what kind of equation are you going to use? For example, I avoided using d as the distance between the two cliffs. This lowercase d, I used uppercase because I knew there will be a conflict. When I use 2d over t, and then here I'm using another symbol, I'm going to have a bit of a problem. Rather, if I call this one lowercase d, and this equation has got lowercase, then it's going to be conflicting. So use some other symbols. This kind of skill comes with practice. So you've got to do a lot of practice when you are solving these questions. And that is exactly why I've given you many questions to solve. Now let's go to the next question. And this is question number 4, where we are given a girl stands 160 meters away from a high wall and claps her hands at a steady rate so that each clap coincides with the echo of the one before. Okay, if she makes 60 claps in 1 minute, what is the speed of sound? Now this is what happens. If you're standing in front of a large building such as the school hall, you find that if you clap the two pieces of wood together like that, you immediately hear your own clap. At the same time, that sound travels from you, goes and hits the wall. When it comes back, you will hear the same clap, right? Only that it is a bit diminished. So if you hear it, you clap again. So you continue clapping like that until when you hear the clap, it coincides with your new clap. That is, you have clapped, the sound has gone, hit the wall. When it comes back, as soon as it reaches you, you clap again, so that eventually you end up hearing your own claps and you don't hear the reflected sound. The echo, you do not hear the echo because it coincides with your clap, and that is what they have described there. She claps, let me see, she claps her hands at a steady rate. Before you can get this steady rate, you've really got to do some practice. And it's good that there are two of you, the person who is going to be listening to your claps and the echo. You're also going to increase the rate at which you clap until your clap coincides with your echo. And then this other person is going to start timing and counting the claps. So he or she can get time for n claps. For example, here we've been told 60 claps in 1 minute. It's a long period of time because you can easily get tired and you can lose the rhythm. But that one is an experiment which we normally do, and it is usually very, very interesting. So she makes 60 claps in 1 minute. So what is the speed of sound? We need to get the time for one clap. The time for one clap means when I clap, that sound goes and hits the wall. When it comes back, that is the time that we want to get. It is referred to as time for one clap. But remember, a clap means the time taken by the sound to move from where you are, hits the wall and comes back. That is the time for one clap. Let's see how it is worked out. It's a very simple one in that I need to get the time for one clap, where I get the time for n claps. So I'll get that time divided by how many claps there are, and in this case I get 1 second. And that is how I get to use v is equals to 2d over t. I substitute 2 times 160 divided by 1, I get 320 meters per second. Usually very, very simple. However, let's look at part B of that question. If she moves 40 meters closer to the wall, now she is 160 minus 40 meters closer. It means it is 160 minus 40. Now she is 120 meters from the wall. And then she repeats, calculate the speed of sound when she finds that the clapping rate has to be 80 claps per minute. Again, I can be able to work out the time for one clap, which is 0.75 seconds. Then when I use the same equation, I get the same speed, 320 meters per second. That question was just as simple as that. Let's go to the next question, which is question 7. A person standing 49.5 meters from the foot of a tall cliff claps his hands and hears an echo 0.3 seconds later. Calculate the velocity of sound in air. This is one of the simplest questions because it's direct use of the equation v is equals to 2d over t, and when you substitute you get about 330 meters per second. Remember, in these calculations we don't have to get the same speed of 340 meters per second. Remember what we said in the first video yesterday, that the speed of sound in air is affected by temperature, humidity, pressure, air pressure, and so forth. So you find that we are getting a range of speed from 320 meters per second to 340 meters per second. That's why you find in one calculation we are getting 320, in another one we are getting 330, like for example in this question. In another one we will get 340 and so forth, or values which are in between that. Like there is one of them that you are going to get 333.3 meters per second. So let's continue to the next question, which is question 8. Now question 8 is a bit challenging, but as soon as you understand what the question was all about, it's not challenging. These two people are standing facing each other 200 meters apart on one side of a high wall and at the same perpendicular distance from it. This is the importance of drawing a diagram, because I said let this person A be here, the other one B here. They are separated by a distance of about 200 meters, but they are at the same perpendicular distance from the wall. That is how the situation is supposed to be on this particular diagram. Now, what is the information given? When one fires a pistol, the other hears a report 0.6 seconds after the flash and a second sound 0.25 seconds later. So that means that this shorter time, 0.6 seconds, is the time taken by the sound which travels directly from A to B. So it covers the distance of 200 meters. Then 0.25 seconds later means a total time of 0.85 seconds. That's why it is longer than the other one. Means there is sound which traveled from A to the wall, hits the wall, and then gets reflected. Here I'd like you to remember the fact that sound, just like any other wave, undergoes a reflection, and therefore it obeys the laws of reflection. The angle of incidence here is equal to the angle of reflection. I hope you can remember this from a reflection of light at plane surfaces in Form 1. So that sound travels from A, hits the wall at this point, and the angle between this line and this line is the angle of incidence. This is the angle of reflection. They are going to be the same, and therefore it travels towards B. So by using 200 divided by 6, we can get the speed of sound in air. The same speed can be obtained by 2d over t. In other words, it's going to travel through x plus x, x plus x, which is 2x, divided by 0.85 seconds. So in the other section, you find that now when it comes to using v is equals to 2d over t, we know the speed from the first part, which is 333.33, is equals to 2x, because the sound travels through x plus another x, over, now the time will be 0.6 plus 0.25. Remember, we've been told here that the sound takes 0.25 seconds later. You know, it is after the 0.6. That is why the total time for that section is 0.85 seconds. All right. And from there, we can get the value of x. But once we get the value of x, we remember that what we have been asked to calculate is d. So we've got to think about this triangle here. Okay. So once we get this x, and this distance from here to here is 200, then from here to here is 100, and you get this type of triangle, right angled triangle. So to get this length, d will be d squared is equals to, I think this one ought to have been, I think I've made a mistake here. Let me just correct that, and then we continue. I think I've solved the mistake. Because 141.6 is the hypotenuse, while the opposite is the one which is 100, and therefore I was supposed to work out the d. It is d squared plus 100 squared, which should be equal to 141.6 squared. Okay, so d squared will be equal to 141.6 squared minus 100 squared. That is the way it is supposed to be, because it is this squared plus this squared, which should be equal to this squared, and that gives me the value of d as 100.3 meters, 0.3 meters. It's not so different from the 100 that we had around here. That is basically how you're supposed to solve that particular question. Again, go through it to see that you understand all the concepts as we have discussed them. Let's go to question number 9. Question number 9, we are told what is the relationship between the relationship connecting the frequency, wavelength, and velocity of sound in air. And this one is very simple. The velocity is equals to frequency times the wavelength. B, an echo sounder in a ship produces sound pulses, and an echo is received from the seabed after 0.2 seconds. If the velocity of sound in water is 1400 meters per second, calculate the depth of the sea. Again, by using the equation v is equals to 2d over t, we are able to see that the depth of the sea is 140 meters. Only that we've been given the speed of sound in water. It's 1400. The second one is that if the echo sounder had produced continuous waves of frequency 25 kilohertz, what would be their wavelength in the water? And by using the equation that we have been asked to write down in part A, we are able to see that wavelength is equals to speed over frequency. We already know this. The speed, we have been given the frequency as 25 kilohertz, which is 25,000 hertz, and it gives us 0.056 meters as the wavelength. The next question is question 11, where we have given that the figure below shows a vibrating tuning fork. The time interval for the prong to go from A to B is 0.005 seconds, 0.005 seconds. And you find that this one is half an oscillation or half a vibration, because this one is a crest all the way to the trough. I mean, for it to make one complete oscillation, it will be from A to B and back to A. So you find that it is half an oscillation. So half the periodic time, 0.005 seconds, therefore the periodic time is, this means seconds, 0.010 seconds. Therefore, frequency is 1 over periodic time. This is the relationship which I want you to remember from waves, because you have already studied waves. The relationship between frequency and periodic time. Frequency is 1 of the periodic time, or periodic time is 1 over frequency. And by doing that, we're able to get the frequency of 100 hertz. How about the second part, the wavelength of the vibrations if the velocity of sound in air is so much? Again, this one tests the use of the equation V is equals to F lambda, and when you substitute, you get 3.4 meters. Just confirm by using your calculator. We are coming closer to the end of this video. Let's look at question 12. In question 12, we are given this diagram here, and we are required to name the compression, the rarefaction, and the wavelength of the waves. A compression is a region whereby the air particles are very close to each other, and they are represented by those lines which are very close. That will be a compression. A rarefaction is a region whereby the particles are spaced out, and it is represented by regions where the lines are far away from each other. So these are a compression, a compression, a compression, a compression. However, a compression is a wave crest. This is a wave crest. This is a wave crest, and this is a wave crest. A rarefaction is a wave trough. So in between, we've got troughs, troughs, troughs. So when we connect the crest to the trough, to the next crest, to the trough, to the next crest like that, we are going to get a full wave. And then the wavelength is from one crest to the next crest, or from one trough to the next trough, right? So that when now it comes to part B, where we are told if the wave front takes 0.1 seconds to travel from A to B, from A to B, 0.1 seconds, we should realize that it has taken 3 periodic times, because a periodic time is a time taken for the wave to make one complete oscillation, and one complete oscillation is one wavelength. So although this one is a wavelength, we can say how many periods do we have here? 1, 2, 3. So 3 periods correspond to 0.1 seconds. So how about a single period? It will be 0.1 divided by 3. And frequency is 1 over periodic time. So 1 over 0.1 divided by 3 will be like 3 over 0.1 hertz. Let me just illustrate that one so that it's clear. We are saying the periodic time is 0.1 divided by 3. So I left it like that. So frequency is like 1 over periodic time. This is like 1 divided by periodic time. This will be given 1 times 1 over periodic time. This is like 1 times, now if periodic time is 0.1 over 3, 1 over periodic time is 3 over 0.1, and that is how we got this value here as the frequency. Okay, So that is how we work out that part. How about the wavelength? If velocity of sound in air is 330 meters per second, again, the use of the equation lambda is equals to f over frequency, we are going to get 11 meters. So it is just that simple. Go through that question again, especially the area about compressions and rarefactions. And then when you join the crest to the troughs, to the crest, to the next trough, you get a wave. The important thing is that as soon as you've gotten that wave, it's easier to identify a wavelength. It's from one crest to the next crest, okay? Or from one trough to the next trough. And then from there, you have to remember that a wavelength usually represents one complete oscillation. The time taken for the wave to make one complete oscillation is called periodic time. That's why we are saying if this wave makes 3 wavelengths from here to here, 3 oscillations. So the time taken will be 3 periodic times. And that is where we get here. I should have written this, that 3 periodic times constitute or adds up to that, so that when I divide both sides by 3, I end up with this equation. I hope that helps in the way I've worked it out. Let's go to the next question. Question 13. A wooden strip presses on a cogged wheel as it rotates at 300 revolutions per second. If the wheel has 100 teeth, find the frequency and the wavelength of sound. The frequency is simply number of teeth in that cog wheel times the revolutions per second. Very simple. And that is how I got 30 kilohertz, which is 300,000 hertz. When it comes to calculating the wavelength, I just need to use the equation wavelength is equals to speed over frequency. And then by substituting the speed that I've been given there, the speed is over here, and the frequency is what I've worked out, then I'm able to get this as the wavelength, 0.011 meters. However, the next question, which is the last question, had a problem. This one's something that is common in our course book. It's not anything that is strange. This question could not be worked out because the revolutions per second of this disk has not been given. How many revolutions per second does this disk make? All right, so that we are able to calculate frequency, because frequency is equals to the number of holes in the disk times the value of the revolutions per second of the disk. So go through the questions once again. The solutions once again. If you look at this video, right at the bottom, there is a way you can run your cursor along the bottom of the video, and you'll be able to see questions popping up. So if you want to revisit a particular question, just put the cursor over there and you will see. The moment that question pops up, click on it, and immediately the video will start playing for that particular question. Okay, I've done that with all of the videos that I've put in my channel, so that it enables you to navigate from one part of the video to the next video. Otherwise, see you in the next lesson, where we're going to look at calculations in the topic reflection at curved surfaces. Bye-bye.